Now for this same question that I discussed in the previous video, what if we use this relationship? Now remember, we used this relationship in the very first problem that I discussed in this section, right? For this problem, we use that inequality relationship, this one. And for the second problem, first I use the alternate series approximation theorem. And then for this one also we can use that inequality that relates the n plus 1th derivative along with the Rn. Now for that, first of all, you should realize that this is the this is the T5 term, right? The fifth degree Taylor polynomial. And from here we can say that the remainder for T5 we can represent it as R5. So to apply the this inequality and to get a certain high upper bound for R5, we need the sixth derivative of fx, right? So now you can see in our specific example, fx is equal to sin x, right? Therefore, the sixth derivative of fx, this differentiated once will give you cos x, 2 times will give you negative sin x, 3 times will give you negative cos x, 3, 4 will give you sin x, and 5 will give you cos x, and then the sixth derivative of f will give you once again negative sin x, right? So anyway, it interchanges between sine and cosine along with these negative coefficients. But anyway, if we get the modulus of x, f6 or any other derivative, you can see that it is the modulus of this sine or the cosine term. So definitely all these derivatives will be less than or equal to 1. Hence we have that the sixth derivative of fx is less than or equal to 1. Therefore we can consider 1 as our m in the inequality. Therefore we have R5 less than or equal to 1 divided by 6 factorial x minus here, as we are taking the Maclaurin series, we have this one. So ultimately what we have is the remainder of fifth degree Taylor polynomial is less than or equal to x to the power 6 divided by 6 factorial. And as we are taking the range of x from negative 0.3 to 0.3, we can find the maximum error that can be caused by substituting the maximum number for the x, right? And you can see that there is a slight difference between this value and the upper bound that we took when we are using the alternate series approximation theorem. Right now, see here we considered we were able to take this number, right? That is, if you carefully follow the steps, we have the upper bound of x to the power 7 divided by 7 factorial. But in the new case, in this new method, the upper bound was x to the power 6 divided by 6 factorial, right? But in the previous case, it was x to the power 7 divided by 7 factorial. So now this is a better approximation than this one, because this is a smaller value, right? So it's way more better than having x to the power 6 over 6 factorial, because if you solve this number you will get 6 zeros as decimal places, where in this case you had 7 zeros, right? So let's see whether we can come up with this same approximation as it was in the alternating series approximation theorem, that is this one. So here what we can do is, now as we are approximating the sine function with this Taylor polynomial, we can even consider this to be equal to the 6th degree Taylor polynomial, because actually there is no 6th power in here, right? Because 6 is an even number and you don't have any even powers for the Maclaurin series of sin x. So you can even write down the same expression as this one, right? It will not make any difference. So here in this case t5x is equal to t6x. Remember, these numbers are entirely decided on the power of x, right? So as we have this relationship, finding the R5 is same as finding the R6, right? That is the remainder of the 6th degree Taylor polynomial. So we can adopt R6 in our inequality. Therefore, to calculate R6, we will need F7, right? So F7 will also be, since F6 is negative sin x, F7 will be equal to negative cosine x. And anyway, when you take the modulus, it will be less than or equal to 1. Hence, F7 is less than or equal to 1. And from the inequality, it says R6 will be less than or equal to 1 divided by 7 times 7, x to the power 7, when x is in between these values, right? Therefore, now you can see that we have the same relationship for the remainder as it was in the previous problem. Now, if you are given with a certain problem like this, you can choose whatever the method you prefer. But here, now, like if we are directly using this inequality, you might not consider R6, but instead you can do it for R5, as we are taking T5, and then carry out the calculation. Remember, in the very first problem, we did it like that, right? In the very first problem, we had the 2nd degree Taylor polynomial here. So we should normally, what we have to do is we just have to calculate the, if it is T2, we should calculate R2, right? Because that's how they are related. But since sine and cosine functions are different, you have this special relationship, right? That's the only reason for being able to maintain the same accuracy for both T5 and T6. And when you take R6 by considering T6, you will get a better result. So it's better than saying that this has, that T5 has an accuracy of this much. And if you say T5 has an accuracy of this much, and if you say T5 has an accuracy of 0.3 7 over 7 factorial, this statement is more satisfying, right? Because it has 7 zeros, where in this case it has only 6 zeros. So this will signify the appropriate nature more than when you express it with this inequality, right? So our alternating series estimation theorem gave a better way with the direct step. But if you are using the inequality, we will need to think a little bit more to adopt R6 for the T5, right? Okay, so simply what we can extract out from this calculation is, if you use the alternating series approximation theorem directly, it will give a better approximation. But why didn't we use it in this question? The reason is, now when you take a number within this interval, let's say if we take 7, right? Then when you substitute it in this polynomial or in this series, right? Let's substitute 7 in here. Then it will be 2 plus 1 over 12 negative 1 minus 1 over 288. Then it is negative 1 squared, which is 1, right? Now you can clearly see that there are two negative terms, one are like close to each other consecutively, right? So here it does not display the alternating series pattern. The plus and minuses will not alternate, but instead you have it as the same plus or minus nature is there for two consecutive numbers, right? Therefore the alternating series pattern is destroyed. So that's the reason for not being able to apply the alternate series approximation theorem. But the good thing is, if x is greater than 8, okay, if x is greater than 8, then this will become an alternating series. So if we are approximating for the values, let's say 9 to 10, then we can use the alternate series approximation theorem for this problem as well. But the thing is, as we are given with this specific domain to consider, within this region there are some x values which will not make this series an alternating series. So we will have to use that inequality in order to get the required accuracy.